All right. Am I working? Okay. So Nathan, am I good to go?
5 and 3 minutes.
Oh, okay. I got 3 minutes. How are you guys doing?
Divine.
I actually have 4 students. Amazing.
You have 3 students. Yeah, I know.
David's saying I don't need this. David knows more math than I do.
I took differential equations. I'm done.
Yeah. We're going to talk about that. Just long enough to know that it exists.
Triple integrals, Laplacian transforms, Taylor series.
Right.
We have Taylor series in trig.
Right. And we will mention that too. I'm just trying to get ahead of myself a little bit. Nah, I don't want to get too far. That's nothing wrong with that. All right. So you'll give me a high sign?
Yeah, you've got 2 minutes.
What can you do with 2 minutes?
What can you do to? Hey, Christopher, how are you?
Hey, got a haircut. Hey, got a haircut. I need a haircut.
The question is, do you know how many hairs I have on my head?
No, I don't, but God does.
But can you guess?
Can I guess? Yeah, actually, I can't. I haven't thought about that kind of question.
Anybody know an approximate amount of?
Well, yeah, you can sit and look at somebody and you can take the square inches of their head. You can look at a couple of representative areas and say, in each area of so much, there are this many hairs, and then you extend that over the thing and you have an approximation, but it's not exact.
It looks
By
like
any
you
means.
have 1 hair per millimeter. Milli-inch.
No, you have to do well. We do it in. Well, we'll talk about that. Talk about that. So, did you watch the one on biology? Okay, just wondered.
Chemistry is finally up. According to Adam.
Wait, is it up?
According to Adam.
According to Adam.
Finally.
So I wanted to put up a thing. All right. Well, we are here for class number 4. Remember, the purpose of the class is this: Introduction to Science and Math, basically high schoolish level, albeit many other people could get some use out of it, and it's meant for homeschooling. So it's a good thing for parents to watch. Says they're preparing their kids. They think about, how do I teach my kids? Where do I begin? And so we did science and the Bible, which I think was great. We did chemistry, which I absolutely loved. We did biology, which I think was pretty interesting. So today we're going to talk about math, or as the British call it, maths. This is the argument. Mathematics, when you shorten it, should it keep the S? Is it plural or is it not? In America, we say math. In Britain, they say maths, just so you know why, because you'll always wonder why people do that. But that's the reason. So mathematics begins very simply with counting and leading to accounting of things. And most of the math that you will find, if you look at ancient Sumerian tablets written in those little wedgy things we call Akkadian or various languages, if you look at Babylonian records, they're keeping account of how many sheep somebody had, how many bushels of wheat they had, how many whatevers that they sold, and those kind of things. That's what they're looking over. So that's what we call today accounting. Excuse me. Accounting is really in the realms of business, keeping track of things. How many chairs do we have? Does anybody know?
120.
Close. But you can count them, and you can know exactly how many chairs that we have on the floor here. So the idea is that you're keeping track of stuff. And the first thing people used, they're digits. So this is why most math or maths are in the base 10, because we're used to 10. I got 10 fingers, so I can easily do 10. I get to 10, I start over, and then I go again. And so that's how people keep track of things. As they got more sophisticated, they began to learn how to add and to subtract and to multiply and to divide. And there were many different types of numerals. Most everybody has seen you know, something like that. I got that wrong. Let's do this. So M is 1,000, X is 10, V, so it's 1,015. It's a terrible way to do mathematics. It's really, you should try it sometime, to add these things together. It's just doing simple operations. And we call these Roman numerals because they were the ones that they used in the Latin days in Rome to keep account. How many did you have? Okay, the only time you ever see it anymore is like when they put the year on some movie, MCM or whatever, it was the 1900s. And that's what they would do. So that's one way. If you look at the Akkadian way, it's equally silly, very hard to keep track. And over time, mathematics developed the ability to count using some very specific numbers. 0 being the first and most important one. A placeholder, so that you could begin to do the decimal system with zeros. And for you guys, this is very simple. You just think of this as like this is normal, but this was not normal for many years. That means 100, because we remember learning the places, the ones place, the tens place, the hundreds place. But you can also write 100 in a different way. You could write it in binary, where you only have 2 numbers. You have a 0 and a 1. That's what we use in computer science. You could write it in hexadecimal, which is base 16, so that you use 16 different numbers. And when you get to you do count to 15, and when you get to 16, now you have a 16, which is a 1, and you start over. So that in hexadecimal, for us, we say that's 11. And hexadecimal, what is that? 17. It's 17. Very hard to understand. And that, if I put a 2 there, it's 18. And so it gets a little hard for people to read because they use the same symbols, so it drives people crazy trying to keep up with it. And I'm not going to spend a lot of time on different bases. I think bases are fascinating. It's something that you probably ought to spend some time studying and some time in your life, because it's really the way we do it. Like I said, computers are based on binary. So every number is written as ones and zeros, because a computer only knows 2 states, on or off. So is it on or is it off? And that on and off state is what drives the way it tells what something is. You can't tell the computer, oh, there's 5 of those. It can only know, is it on or off? So in order to write 5, you have to write in binary. It would look like, what would it look like? It would be this, not 21. That's hex or something else. In binary, it would be 1, 2, so it would be 101. That would be 5. Just 5 would be written as 101. Okay? Because this is a 4's place, a 2's place, a 1's place, 2, 4, 8, 16. So it doubles. Each space is double the one before. And then you write them out. So you could, you could see what's the weakness of doing binary numbers. They get very, very long, very fast. But see, computer doesn't care. But it only knows 1 and 0. It's the only things it knows. So you have to do it that way. So the second thing that we developed, besides a 0, to say, hey, that place has 0, was the decimal. So in our way of writing, if I write this, if I put that little point there, what do I have? I have 10.1. So I have a fractional part of whatever I'm counting. That number, that decimal place, is huge in the way in which we use numbers today. You can't do everything with fractions. It just doesn't work. And it's not as quick and it's not as easy. So this decimal place. So I told you that the 2 great developments in numbers, the 0, just that concept of holding a place with nothing, and the concept of a point, a decimal point, talking about fractional parts. Huge advances in mathematics. Now, when I do pure mathematics, absolutely pure, do you realize they don't like decimal points? They like fractions. Is that not true? They like fractions. Okay? But there are certain numbers you can't write with fractions. Anybody know an example besides these two guys of a number you can't write with fractions? The most famous number that you can't write with fractions is the one that starts off like this. Anybody know what? It's pi. We call that pi. It's classically written as pi, and it goes on forever. There are people, you can find them on the internet, they'll quote pi to you, sit there and quote pi to you to 500 decimal points or something. I don't know where it's been calculated to these days. The reason is because it's a decimal that never ends, and fractions can only approximate it. So decimals are considered to be, a little more accurate in some ways, but less accurate in others. And we're going to talk a little bit in a bit why fractions are important. But I'm just preparing you for where we're going. That's what math is about. Most people in their life don't do any more than this. They count. That's what they do. They figure how many have I got, I got $10, I'm buying something for $9, I have enough money to buy it with. That's all they know. They don't need fancy mathematics to do what they're doing. And we'll talk about the levels and why certain ones are important in a moment. But I want you to understand that this concept of a zero and the concept of a decimal point are relatively modern inventions. That's something that it's in recent times that this has been figured out and has been used. When I say recent, I mean, back, a couple thousand years, something like that. That's relatively recent. And really, probably even sooner than that. I don't know the date. I didn't look it up, but get the idea. It was probably in the AD times that we were really doing this sometime. Okay, so that's the basics. These things are called operators. When you write equations, you use these operators. And there is one operator that I always taught my kids was the most famous and most important operator you could ever do, and that was the equal sign. Okay, everybody's seen one, right? 2 plus 2 equals 4. And we say that they're equal and they're equivalent. We've got the same thing. They don't look the same. If I write this as 2 plus 2 equals 4, they don't look the same, but they are equivalent in what they represent. It represents 4 chairs. You get 2, you get 2, I have 4 chairs, right? That's basic counting stuff. So when I start off talking to my kids, when I talk to them about algebra, I would emphasize to them what I called the basic rules that you needed to know. And the first rule was this. There's an equal sign. And if I have an equal sign, I can do the same thing to both sides of the equation, and I did not change the fact that they are equal. No matter what I do, if I have an equal sign and I could have this super long equation, if I do the exact same thing to both sides, they remain equal. Okay? That rule, amazingly, people struggle with, but it is the one that you've got to get first if you're going to do anything in what we term algebra. So when we move from accounting to algebra, we're starting to do something different. It's a different way of looking at stuff. It's looking at the world and describing it with math. Remember up here, we were just counting the world. I got 1 vacuum cleaner, I got 7 students, I got 120 some chairs, I got 1 camera, 1 whiteboard, etc. I'm counting. Algebra, I begin to describe my world. And the first thing I have to be able to do is use an equal sign and understand what it does. When I take this and I multiply through those things, I will get something similar. In this case, I'll get 6 plus 6 equals 12, and 6 plus 6 is 12. And so they're equivalent. I can do the same thing to both sides of an equal sign, and it transforms the equation that I'm looking at into something else. That's what it does. Now, this is pretty elementary. Anybody who's taken any math of any kind at all should know this. But algebra is the math that is the first one that you do that starts to make you, what we might say, educated about how to use math. It's the first. And the first rule is this. The other rule that you always have to know, beside with the equal sign, is that whatever is on these two sides, whatever you're doing, you can multiply anything, no matter what it is, by 1, and it does not change. You can divide by 1 as well. It does not change. So the first rule is equal sign. X equals X, or 2 plus 2 equals 4, or 3 equals 3, whatever it might be. And I can do the same thing to both sides. Second rule, I can multiply anything by 1. Now here's the interesting thing about 1. If I go, this pen is dying. If I go x squared plus 2x minus 3 over x squared plus 2x minus 3, what does that equal to?
1.
It's equal to 1. Why? Because anything over itself is equal to 1. That's what it is. And when I understand that, I can take this equation, I can multiply it by one of my sides, and it does not change the fact that they are equal because I multiply by 1. This is two simple numbers. Equals is the operator, 0 matters, we're going to get some more of that, and 1. 0. There's one very important rule about 0. You cannot divide by 0. When you try to divide by 0, math breaks down. It's undefined, it does not work. The biggest problem with 0 is sometimes people divide by 0 in an equation, don't realize they're dividing by 0 because it's written in some other form. So they don't realize that it's equivalent to 0, and they divide by it and think they've come up with a solution, and somebody goes back and says, excuse me, this that you divided by actually is equal to 0. Oh, it's undefined. So you got to know the concept of an equal sign, got to know the concept of 1 being in many forms. 1,000 over 1,000 is 1. A billion over a billion is 1. Some fancy equation over itself is 1. And 0 you cannot divide by. This becomes very important in higher math because there are many, many, many proofs that are hard to do because you can't avoid dividing by the potential of 0. It might be 0. You're not sure if it's 0. It turns out that it's 0 if you keep going, those kind of things. So it becomes very hard. Now, algebra is what most people in my day took as freshmen in high school. In today's world, they often take in 8th grade. That's the most common time. And with this new math, I have no idea what they're doing. Can you hand me a couple of Kleenexes there? I'm going to erase some of this. So, algebra. To finish up, the other important thing about algebra that we always have to know, so if you remember, equal sign, 1 and 0, being the concepts that everybody has to know, is the concept of a graph. A graph is when you take and you represent something as a line or a curve on a space. Now, most of the graphs that you'll do in algebra are two-dimensional. You've got what is commonly called an x-axis and what is commonly called a y-axis. Y-axis traditionally going up and down, x-axis going horizontally. This concept will follow you through every kind of math you do. It's just that when you get up higher, they start doing it in 3 dimensions, and they start doing it with 3 dimensions with an imaginary dimension, and then they start doing it, it gets kind of crazy after a while and gets hard to picture. But these 2-dimensional, everybody should be able to picture this very, very easily, and it'll become important when we eventually get to talking about data and the way data is represented, because graphs are a huge part of that. So this is when I take a point, commonly called x and y. If the x is 1 and the y is 2, I go 1 and up 2, and there's my point. Okay? And then I'm not going to do all this for you because this is something you can go get online. But the equation of a line is commonly known, y. The y is equal to the slope times the x plus the x-intercept or the b, and that would be an equation you would make. You know, if you had a line, every line is represented by an equation of this form.
B is the y-intercept.
Y-intercept, I mean, you're right. Forgive me. So, in algebra, once you've got the basics of how an equation is written, you understand what an equal sign is, you understand what 1 is, you understand you can't divide by 0, you have to be able to graph. And you should, if you haven't ever done it, you should be studying graphs. How do they look? What do they represent? Most of the graphs that we see when we talk about data are going to be things like number of cars built year over year, you know, those kind of things. They make lines and graphs, and there's scatter points of data, and what does that data mean, and statistics and all that. But it starts with this simple thing, y equals mx plus b. Very easy equation, but it can be written in so many different ways, and that's a big part of what you learn in algebra. You learn to manipulate these equations, and then what gets even more fun is you start getting lines that are curved. You start off in algebra with lines that are curved by in very specific ways so that they're representative. They're not just random curves. They're curves that go because of the way the equation is written. You start using quadratic equations where they've got x squared in them and things like that, and you start putting those together, and you learn how to solve those equations and break those equations down and figure out what they mean, and you pound away at that over a couple of years. Traditional school algebra was a couple of years, and for people who do it well, they've done more than that and spent time understanding where these things come from. So that's algebra. I don't know any other simple way to present the basics of algebra than that. So I used to drill my kids, what are the 4 rules of math, thing like that, and then just get them to spout them off at me. And then I forgot what they were because, you know, I made them up on the fly. But the idea was to get them thinking in terms of equations. Equations are huge. The simplest equations can be done by just a little guy who's learning how to count. When you say blank plus 2 equals 4, what's in the blank? Okay, what if I put an X there? Does it throw you? Okay, it's not a real problem. You guys can all do that stuff. So that's the basics of algebra. Now, how many times do you have to do y equals mx plus b? I think, you know, hundreds of times, because it can be written so weirdly that you don't recognize it for what it is. And the m could be not a number, like 2. It could be a huge, weird equation that's the m. But when you begin to represent and understand what you're looking at, you can do it. And then people will teach you how to do that. Nowadays, you can go online for math, and you can go to some place like Khan Academy, and they'll teach you everything. It's all there. Is it the best? I don't know. Is there another one? Do you guys have another one? You go there and you say, I want to understand the equation of a line. They'll have video after video after video on how to do it. You know, you get an algebra book, and they'll have chapter after chapter after chapter on how to use it, that kind of thing. So that amount of math is what most people will use. That's it. They will never need anything more than that. If you understand the basics of an equation and you understand the basics of counting, you're on top of it. If you want to be an accountant, you never have to do anything too much more complicated than adding, subtracting, multiplying, and dividing. That's it. Maybe occasionally, there's, you know, they have to use graphs and things in their spreadsheets and stuff, and so they'll represent data that way, but they're not really doing any complex calculations. So let's move on to the next thing. The infamous, most importantly, this is interesting because it's actually called the calculus, which is quite interesting when you think about it. It's got a proper, you know, it's a very proper name. It's like, this is Elijah, this is the calculus. You know, it's very specific. This was jointly developed by a couple of people. One of them was Newton, the other guy, I always forget his name. Who? Anyway, it doesn't matter. Leibniz, that's right, that was the name. They both worked this out separately, and then it was all brought together. And the whole idea of the calculus is you take your algebra, and I didn't talk about geometry. I may, if I have time, just talk about geometry. Your trigonometry, which is your basic description of things that modulate in rhythms, okay? And you take all of that, and you take those things together, and then you develop this thing called the calculus. So what, am I going to teach you calculus thing? No, I am not. I'm not even going to try it. But what I'm going to represent to you is that calculus is the place you go. It's where you want to go in math to begin to understand. Everything that is done today that you look at and go, wow, that's amazing. You know, that new system for running the sound, that incredible nuclear, calculus is inherent in all of that. Not algebra, calculus, okay? Because everything that is done has to be done in very specific ways. And when we talk about, remember we talked about the graph, and we talked about the way that you take a line and you could represent a line. What calculus allows you to do is look at the area underneath a line or a curve and look at any point and how it's moving at any time very, very simply. And so the terms that you'll hear about in calculus is you hear about the derivative, and you'll hear about the integral. So Christopher, how do you define the derivative?
Slope of the tangent line.
So the derivative is a slope of a tangent line at any point along any curve. And the thing about these curves, it could be something that is just weird. And you can go to any point along here, and you can take the derivative, and you will find the slope at that point. And that's very important when you're applying it to certain functions. Do you use derivatives every day in what you do?
Yes.
Every day, he has to use derivatives because he builds buildings that have to take stresses and not collapse on you. Okay? That's basically it. The integral is when you look at this curve and you take a specific area of this curve and you look at the area underneath it, and you can figure out what that area is. And that allows you to look at how much of a thing has been covered. And it's pretty intense stuff. The beginnings of it are actually fairly easy. Any one of you could sit down in a calculus class and understand how to take a simple derivative of a simple equation. It is not very difficult at all. But that's where you want to go. I always like to tell my kids, I would always tell them, look, if when you've done calculus, now you really understand what people are talking about when they talk about science. Up to that point, you don't really get it. It's not, it's just sort of, it's like drawing stick figures and calling them people. It works up to a point, but calculus is like 3D full motion animation in comparison to stick figures on a flannel graph, okay? If you get the idea. And you have to begin in calculus with learning the basics. How do you define a derivative? Where did it come from? How do you define an integral? What does it mean? And there's a whole lot of math to explain it. And then from there, you go to, now let's do the really complicated stuff. You know, how do we represent in mathematical form a three-dimensional object that is not equal on all sides? How do I represent that? It becomes very complicated. And it can get as complicated as you want to get it, and you can sit with David and Christopher and try to do the math that they've done and just sit there and go, are you kidding me? It's like it's out there someplace. Only a few people really need to know that level. You just don't need to know it. I don't use it in what I do. I use algebra every single day. Not just counting, I use algebra because I got to figure things in relation to other things in a way that I use algebra all the time. We use calculus in medicine when we talk about representing things, the tools that we use, all those kind of things. You know, a thermometer today, if you walk into the doctor's office, they got these $500 thermometers that you would never buy for home use. The fancy little things. They use calculus to take representative samples of the temperature coming across the probe and figure out what the temperature is. That's what they have a mathematical formula inside of them that does it. So they can do it quick. So you can take the temperature fast. Because when you got screaming children, they really don't want you to hold it underneath their tongue for 3 minutes to get a good temperature. So you have it, it's designed to go fast, but it uses math to do it. Okay? So they're very complicated thermometers. So that's calculus. That's just an introduction to what is calculus. Okay? That's all that is. Believe me, if you haven't gone through algebra and you haven't gone through geometry, you haven't gone through trigonometry, you can't even do calculus. But once you do calculus, you never want to do the rest of them because it represents everything. And you can use calculus to do all the things you do with algebra. You just wouldn't do it for most people because they wouldn't understand. So when I took physics in college, there were in my day, there were 2 physics courses. The one for physics majors and the one for the rest of us. And I wanted to take the one for physics majors, but you couldn't fit it into the schedule for somebody who at the time was doing both a biology major and a chemistry major at the same time. I couldn't add in physics level calculus, or physics level physics. So I had to take the sort of dumbed down one. So you can do physics with algebra, and that's what they often do in high school. But most physicist people will tell you that it's a complete lie. Everything about it's a lie. It's not even true. It's just a terrible representation of what is actually going on because everything in physics is actually done with calculus. Is that true? True statement? True statement for those that have done it? I've never done it, so I can't look at you with conviction and say that's absolutely true, like the guys who've done it can. But calculus is where you want to go. And it makes a difference. And when you talk to people about science and math who've never had calculus, it's amazing how there's just this lack of understanding. They just don't get it because it's not their fault. They just never did it. So I would like to see everybody take at least a calculus course. I wish that I'd taken more because it's pretty fancy and a lot of fun. Okay, so let's talk about something fun that has to do with math, because every one of these things we like to talk about what this science means, and then how do I deal with it in a world where I've got the Bible on the one hand and people in science telling me that the Bible is false, and people in the Bible tell me that science is stupid, and I got all these things. I'm trying to reconcile these competing ideas that are wrong. The fact of the matter is, we talked about in science in the Bible, it's understanding that science and math are very good representations of certain things, but they're not the whole picture. When God, you get everything. And so what I make this emphasis when I talk about algebra versus calculus, think about God. We go up to multivariable calculus, we go up to differential equations, which is even higher than that, I think, and we go up to the cutting edge of mathematics, the cutting edge of the physics guys who are doing string theory and all this stuff. And God sits way beyond that, and his understanding is so far beyond that we haven't even close to caught up to him yet. That's really the truth. And when you know calculus, you look at algebra and go, oh, that's what I used to do when I was a baby. Then you do differential equations, and you look back at calculus and go, oh, that's just the beginner steps of math, right? And yet God is still so far beyond that because his understanding is perfect, because he made it all. And ours is finite, and we talked about that in science and the Bible, in understanding that, yes, science works really good for this physical world in which we rely and which we understand, but when we put God into the equation, it's much bigger. So let me give you some examples of where that fits. If I'm going to look at you guys here, and I have a loaf of bread, okay? I got this loaf of bread, and we're all going to sit down to eat. And so I need to take that loaf of bread, and I need to come up with a way to divide it amongst us. And if I want it to be even, there are ways to divide a loaf of bread, depending on what I want to do. Usually it's pretty easy to divide it into half, and then I could potentially divide the halves, we'll say, into half, and I can kind of get close. But the ends are not as big as the middle, and so if I was to seriously divide this loaf of bread, most of us just, we just cut it and do the best we can, and we really don't care about the details. But let's say that it was important that I had to do it as exactly as possible. Well, I could use, some algebraic equations to figure out how big this is compared to that is. I could use calculus to do it much faster. Not that I would ever do this, but you get the idea. But let's think about what Jesus did when he needed to feed everybody with a loaf of bread. He didn't take a loaf of bread and look at it and say, the accounting way would be this. I have one loaf of bread, I have 7 people, we'll call it 8 people, I got to divide it into 8 pieces so that everybody gets some. He had to take 5 loaves and divide it amongst at least 5,000, maybe 8, maybe 10, maybe 12,000 people. And he had baskets left over. Now, account for that. Count that up and figure out how that worked. It doesn't work. It's not what we're doing. See, mathematics is limited to a concept of numbers that we made. And it's internally consistent. When you take math and you keep it in the realms of just basic mathematical principles, it is always consistent. It's 100% accurate in everything you do. Now take the real world and apply mathematics to it and go to the level that people go to. You can get closer and closer and closer and closer and closer to perfect representation of the real world. But would you agree with me? At some point it breaks down. At some point it breaks down. It doesn't work. Even if you just take pi, it's a number that represents the ratio of the circumference of a circle and its diameter. It represents this ratio or fraction, and it goes on forever. It's a never-ending number, and it's not the only one. And there are lots of things. You can go on and look at math puzzles and things like that, and there are tons of weird things in math that don't make a lot of sense to our minds that happen. But how do you do that? And when you go down to the super submicroscopic level, and I never got to do this, but you go down to the calculus level of physics and try to do electromagnetism, down at the super submicroscopic level. It's so complicated, so weird, and apparently, at the end of the day, it's possible I could take this stool, throw it at that wall, and it would pass through without breaking the wall. Theoretically possible. Is that true or not true?
More yes than no.
More yes true than see, again, physics guys. You get down to that level, it is, to me, it's ridiculous. Every time I throw that stool at that wall, something's breaking, okay? That's what's gonna happen. And it's never been different for anybody in experiential thing, whatever. But you get down to the math of these things, and there's the possibility, we'll just say a coin, I can take a coin and throw it and go right through the wall without breaking the wall. The possibility of that happening exists within the mathematics down there. Okay, is it true or not true? Nobody really knows. Nobody knows what's going to go on. It's just craziness. Jesus took these loaves of bread and he multiplied them. He didn't just divide them, which is what we do. He multiplied them. He made them more than they were. Now explain the accounting of that. Look, I had so much flour and I had so much water and I had so much sugar and I had so much yeast and I made so much bread. A baker knows. If I take this much flour and I take this much water and I take this much sugar and I take this much yeast and I mix them all together, I'm going to get this many loaves of bread. I mean, you watch a recipe. We've all done it, right? Jesus takes that loaf of bread that's made out of a finite amount of flour and a finite amount of sugar and water and everything else. He takes that loaf of bread and he feeds multiple people of it so that they have more than enough and they're bringing up baskets. That's how superior God is to the finite world that we live in. And it's important to understand about math, that math is a really good method of accounting for things that we can see. Counting the number of chairs, counting the stress on that beam, and figuring it out in a number representation, how much stress there is on the beam that's wherever it is in the wall, okay? And you can use math to represent those things, but it's never perfect. Is it good enough? Yeah. One way to do it is if the beam needs to bear so much stress and you're really not sure, you just over-engineer it, as we call it. You make the beam stronger than it needs to be so that it doesn't collapse, right? And then, you know, like when the Twin Towers in New York's tragically collapsed and all those people were in them, but you know, when those collapsed, nobody expected them to collapse at first. But when you go back and you apply the math, and you look at it and go, oh, they looked at the conditions, the jet fuel and the fires and how much space, and they looked at the conditions. Oh, it all made sense. Does it make perfect sense? It makes perfect sense. But at the time, I don't think anybody expected it, because you don't send the firefighters up in the building when you expect it to fall down. They didn't know that it would happen. They didn't realize, because nobody planned for that kind of stress on the building. They hadn't thought of it. Well, that's just finite things. How many things does God know that we haven't thought of? How many things are going to happen that we haven't thought of? God knows. So I wanted to stress that when you think about math, and people will tell you, well, I love math, and math is great because it's 100% accurate all the time. Yes, internally consistent within itself, it is. But it's still only a representation. A good way to think about it is I started to use the analogy, if I draw a picture. If I got up here and I'm going to draw a picture of David, and I started drawing a picture of David, it would not look anything like David, because I'm not an artist. But I could put a couple eyes and a nose on it, and a mouth, and maybe a beard and some hair, and I could say that's David. If we got Randy down here to do one of his cartoons, it would look more like David. You know, if we got Cindy down here to do it, it would maybe look even more like David, and somebody else, maybe who's a great artist, and look even more like David. Okay, and they can do it. But it's still not David. It's just a representation. And math is just a very internally consistent representation of counting and seeing how accounting affects the world that we live in. That's what math is. So that you don't have to be buffaloed by these guys, well, you know, math is so 100% effective, and it's always right, and it's so beautiful and perfect, and all of these things. And yet they'll say, well, and it's just not that way. I mean, people pray and it doesn't happen, and all of these things that they don't understand, all the variables. They don't understand everything that's going on. Neither do we. We're just not that smart. What we learned, though, was God told us to put our trust in Him. And no matter how smart we get, no matter how educated we get, no matter what level we get at representing the things of the world, whether it be in chemistry or it be in biology or it be in math or be in physics or it be in any other scientific discipline, we're still short of who God is. Okay, now I did a poor job of that, so I just want to say one more time, this is important about math. Math is beautiful because it relies on a couple of assumptions and the representation of counting things. And within itself, it is absolutely beautiful and 100% consistent. Absolutely. It's just when you begin to take it to represent the real world as if math, you know, people will talk about math as if it comes from the real world, and there's some of that that's true, like pi. You know, it comes from the real world. If you take a circle and you measure it perfectly, you take its diameter and you measure it perfectly and you do it, you would begin to get a number like pi. But you have to measure it. In order to really do it, you have to measure it to that level. You know, you ever taken a ruler and measured something? And you look at it and you kind of eyeball it. Well, I think it's 3 1/4 inches. Somebody else comes along, no, it's 3 3/8. You know, and then somebody else comes by and says, no, it's 3 and 16 or 15 30-seconds, and you begin to look at the level of measurement you do, and you get closer and closer and closer, but you know none of them is exact to the level that people talk about calculating pi out to 500 decimal points. I mean, are you kidding me? And that's the important thing to understand. One of the things that's beautiful about calculus is you don't have to be that accurate. The accuracy is all built into it. It just doesn't, you know, and it's good enough when we talk about significant figures in chemistry and how much do you really need to know? Do you really need to know it to the 10th decimal place? Do you really? No, you don't need to, all right? Think about your TV screens. Let's just use that as an example. When I was a kid, it was black and white. Then I remember we got color, and that was, I mean, compared to what we see today, it was ugly. But we didn't know that then because that was better than anything you'd ever seen. And then the TV screens became more impressive and better, and they were constantly doing things to improve it. And then they switched over to HD, right? And now you got 780, and then you got 1060, and you got all these various levels of screens or whatever. You got 1080p and whatever. What are they doing? They're making the screen better and better and better and better. But is it still live? No. No. When you look at it on your computer screen, it's not the same as being here, right? It's just not the same. It's better than it was. It's clearer than it used to be. But that's what math does for you. At some point, it's silly. You don't need to do it anymore. But that's how it works. Okay. So, last thing to say about math. I'm going to talk about this. And I kind of alluded to it. I just want to do one last thing. The quality of a thing versus a quantity of a thing. People will often call this qualitative and quantitative. This is a very, very important concept in science and math, so I just kind of wanted to throw it in here because it fits with what we're talking about. The quantity of a thing is what we're talking about. How many do you have? Okay, I've got 8 of us here. I got these 8 people that are sitting in these first couple of rows and standing here, these 8 people. Depending on our quality, we can move a certain amount of weight. If we all picked up backpacks, we'd all could carry different sized backpacks. So the quantity is we got 8 people, but the quality is how much can you do versus you versus you versus you, right? To get the job done. Quantity is amount, quality is how good is that amount, the qualitative aspects of something. And that's, it's a poor representation, but you get the idea. You're going to hear these terms a lot when you talk about math. Is that a qualitative thing or is that a quantitative thing? Qualitative, you have to evaluate. You have to evaluate how good something is. You have to evaluate, does that work? Quantity, there's always 8. Quantity is math. You can always measure that. But the quality of a thing becomes a little bit harder. And it requires observation, it requires understanding, it requires knowledge of the subject to be able to decide what's the qualitative aspect of this thing and what it's going to do. Because it varies from person to person and situation to situation. I can carry a heavier backpack in the cool than I can in the heat, for example. All kinds of issues that come into it. And it's just representing this concept of quality versus quantity. And math is extremely good at what is the quantity of a thing. It can represent quality in some ways when you talk about what stress levels something can have or how material is. But that's measurable, quantitative material science. Quality is when you don't have quantitative science to represent a thing, and how do you do it? So it's just another way of representing this difference as we're talking about it. What goes on in math that is so internally consistent that it looks so beautiful and people will look at you and tell you math is superior to God because math is always exactly the way we expect it to be. If I do the equation, it's always the same. And that's because it's all built on the foundation of just a couple of little assumptions. Just very simple, very, very simple assumptions. The ability to count something and then representing counting numbers is really the first assumption. And what does that mean? And then I just showed you that Jesus took that whole quantitative issue of ours and he just destroyed it. He took our piece of bread we were trying to divide amongst people and he multiplied it amongst people. He did something we can't do. Well, we can in him, but that's a whole other concept. Okay? So any questions about math, especially from you guys? A derivative? Oh, derivative. A derivative is when you take an equation of a line at a point and you want to figure out what the slope of that line is. How fast is it rising or falling at that particular point? So the basic that I remember, my guys will laugh at me here, but if I take, a line that is x squared, okay, that means x squared equals y. And I just take that line, and I look at that line and where it goes. It doesn't go like that. Okay? If I do that, so I've got x is 1, y is 1, x is 2, y is 4. And so this thing goes like that, right? And at any point along that line, if I take my x squared and I take the derivative of it, if I got this correctly, the derivative is 2x. So at any point along that line, if I take 2 times the x, I know the slope. Is that correct? Yeah. I got it correct. See, I still know a little bit of this stuff. And that's the slope. So that's the derivative. This is the simplest derivative you'll ever take. The derivative of x squared is 2x. It's ridiculous. All you have to do is take the exponent, subtract 1, and move it to the front. And it just so happens that x to the 1 is x to the 1. Okay? So I didn't write the 1, but that's what it is. If it was x cubed, it would be 3x squared. Is that right? So, I mean, how easy is that? You can teach a kindergartner practically to take a simple derivative. But it's extremely powerful. And it gives you the slope of that line. So you can say, well, at this point in time, what would the slope be? So when is that important? Can anybody name me something that they ever read about or heard about to where knowing this kind of data would be extremely important? Population. Well, population, maybe. It might be. Rocket science. That's why they used to joke about rocket science, because when you take the trajectory of a rocket, it's starting off with a certain amount of thrust, and there's a certain amount of resistance, and that resistance is decreasing, and the thrust is changing, and the rocket is changing in its trajectory, and it's calculus all the way along the whole thing. And then you got to get out of the atmosphere at a certain escape velocity and be heading in the right direction when you do it, and you got to understand derivatives like crazy. And you know how they did it back in those days? Slide rule. Use the slide rule to take all the derivatives. Don't ask me how. They were amazing. So, I mean, they did, and NASA had, after they went to the moon, I think they got one of the first computers. Filled an entire room, and it could do less than your calculator. And, but they use slide rule. In the movie Apollo 13, they did such a great job of showing these guys, they're all sitting there checking the math, because see, they had no computers to check it, so that you had all these eggheads check it, right? So there's a whole bunch of guys doing there, and they're all using their slide rules and check, 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 check. Everybody agrees. The math is right. And that's how you did it in those days. It's pretty incredible when you think about it. We flew to the moon. Nowadays, we got these super powerful computers. Our phones are more power than they even imagined ever having in those days. Our phone could run a Saturn V rocket and wonder what the fuss was. And yet we can't go to the moon anymore. So, you tell me. You tell me, and we'll both know how all that works. I was told, oh goodness, it's close to 40 years ago, was told that in today's world, if you asked NASA to rebuild the Saturn V rocket, that's the one that was able to boost enough payload to go to the moon, they could not rebuild it. They did not know how. There's no plans. All the schematics are missing. Nobody has them. All the parts that they used that you don't exist anymore. You can't even buy the parts. They couldn't rebuild a Saturn V rocket today. Not possible. Somebody could sit down and try to build a better one, but by the time they had built it, it would be so stinking expensive that nobody can go. And so anyway, it's changing. That was 40 years ago. Now, they're building these SpaceX ones, but I don't think they still got anything that can go to the moon. They can get up to low Earth orbit is about all we can do these days. It's stunning, isn't it? All right. So I hope, especially for you guys and anybody who's watching this in the future, when you talk about homeschooling your kids, and you think about mathematics, think about what I want to teach people. How do I want to begin to talk about math? That you'll just understand these basic principles. And each one of these, I could break probably each 2 minutes into a whole other hour lecture. We could spend a lot of time discussing it. Math is fascinating to me to just read about. Now that I don't have to do it for school, I read things about it. I look at how it works. Where does it apply to certain things that I do? I talked about in chemistry, I'm just going to loop this back to the chemistry one, talked about nuclear magnetic resonance that came out of the magnet, that became magnetic resonance imaging, which we now use. I mean, that's all super high math. That's what that is. It's taking and repetitively doing a very complicated integral over curve of data that you get over and over and over and over and over again to eventually arrive at an image. It's extremely intense. But even that, the equation they use, it's basically brute forcing something that anybody who's done higher math can do. I mean, have you guys ever did a Fourier transform? Yeah. They've done a Fourier transform. At some point in their academic career, they had to sit down and do Fourier transforms. The difference is the computer does it 1,000, 15,000, 150,000 times in a very short period of time to fudge all the background noise out and find out what's really there. And so they just repetitive. So have you done anything more complicated than a Fourier transform? Yeah. So that's relatively simple math to people who've done physics. I've never done a Fourier transform in my entire life, but I've used lots of MRIs. And so I've looked at lots of them and I know what they show. So that's how it's done. Somebody sat down and figured that out. So what I want you to know is that when you move forward in math, and I want the homeschooling parents to know, as you think about this, don't let yourself be fooled. Math is extremely beautiful, extremely consistent within itself. But math is not the be-all, end-all answer to the problems of life. Jesus is the answer to life, because in him is life. And he gave us life and life more abundantly. This is what Jesus did. And math is just a representation, and a very poor one at that, albeit much better than it used to be. As we've learned more and more, we get closer and closer to finding out that God's still farther out there than we ever imagined. Okay, that's the end. Thank you guys for coming. So we will try, next time the goal is to do data and statistics and stuff. If I can ever get together with Christopher and sit down and spend some time at it, because I need help with this one. And so we'll see what we can do. And then after that, I've thought about doing physics. I've thought about doing computers. Yeah. I think we'll try. And David's going to help me with physics. All right. Love you guys.